Hi everyone! In this video I wanted to talk about a really fascinating figure called Lissajous Curve. What is special about it is probably the relative simplicity of the definition compared to all the construction, interpretation and connection that can be made from it. This is like an inexhaustible source of surprise and discovery. However, it isn't very popular. For this video I propose to show you what I think are the most fascinating facets of Lissajous Curve. So what are Lissajous Curve? Actually, everyone has an intuition without any mathematics concept. I will begin with some music. In music, when you hear a note from any instrument, you hear a sound signal pulsed at a certain frequency. The higher is the pitch, the higher is the frequency. And when you add a second note simultaneously, your ear is very sensitive to what is called in music an interval, which is the ratio between the two frequencies. A ratio of 1 is called unison, a ratio of 2 is called octave, a ratio of 1.5 is called fifths, and a ratio of 4/3 is called the fourth. One way to represent these two notes is to show the addition of sound signals. But if instead we take the fast diagram, or in other words, we take the signal of the first note depending on the signal of the second note, we will get a Lissajous curve. So here is our definition. Lissajous curves are the resulting trajectory of a point whose vertical and horizontal components are a sinusoidal motion. Actually, this is more another way of representing oscillating phenomenon rather than absolute new curve coming from nowhere. And the only parameters of these curves are of course the relative ratio and phase of the two sinusoids. Now let's go back to our musical intervals and see what Lissajous curves do like in terms of intervals. I don't know if it is just me, but I feel like these curves are really close from what I hear. This is the intuition I was talking about. Okay, now with a better understanding of Lissajous curve, let's play with the second parameter, the phase. As you just saw, if we take Lissajous curves with a ratio of 2 and an increasing phase, it seems like a 3D shape is rotating. That's because there is another way to define Lissajous curve and the construction is very intuitive. Imagine that you have a sheet of paper with a sine wave drawn on it. And then you roll the paper so that the scene overlaps on itself. This will give you a sort of sine crown around the cylinder. And if you take a 2D projection of this curve, this will give you back a Lissajous curve. I feel like this sine crown is more accurate in what a Lissajous curve tries to approximate. It is as if you got access to the full picture. In the following, I will refer to Lissajous curve as a 2D or 3D curve indifferently, since they both look very similar. We have seen a lot of information so far, so let's focus on this new construction of the sine crown. We saw that the phase parameter is acting like a rotation of the sine crown. But what about the ratio parameter? Let's begin with integer ratio. Here are the corresponding Lissajous curves to the integer ratio from 1 to 5. It seems like the integer number of the numerator is related to the number of peaks appearing on the crown. Okay, that was pretty easy. Now what about fraction? Here are ratio numerator of 5 with an increasing denominator. Numerator is related to number of peaks, it is still the case here, but what about denominator? This one is not trivial. But if you look closely, each time the denominator increases, there is one more intersection on the Lissajous curves from a consecutive up to down curve. And this leads to the relation that number of intersection points plus 1 is equal to the denominator. So let's try this quick theorem in another example. Here is the curve of 19/8. And now let's count the number of intersections. That's it. 7 plus 1, we found 8, so this seems to work. So we just saw ratio in terms of integers, in terms of fraction, or rational. Let's see now irrational number. If you don't know what an irrational number is, think in terms of music interval. If an interval was irrational, that will mean that the two notes will never meet after the start. If you take octave interval, they meet 1 time every 2 periods. For the fifth, it's 2 times every 3 periods. And that means that irrational number can be expressed in terms of fraction. Now let's see what happens if I draw a square root of 2 ratio for Lissajous curves. As you might have guessed, the curves never closed. I find it very fascinating how Lissajous curves can give intuition about number properties. Like for rational numbers, we usually learn that decimal sequence is looping, and here the Lissajous curve is looping too. And for irrational number, decimal sequence doesn't loop as well as Lissajous curve. So now let's see one more facet of Lissajous curves, and not the least. We go back to the 2D representation, and instead of sine wave, we take triangle wave. These have slightly impact on the resulting figure, as you can see, but the intersection remains the same. And now, look what happens if I draw the figure as the time increases. And now we are seeing the curve for an increasing ratio from 1 to 2. I think that you have guessed, this is the trajectory of a ball in a square pool table. Who would have guessed that a ball bouncing into a square has something to do with oscillating phenomena like music interval? Here the only difference is that the ratio parameter is actually the slope angle to hit the ball at the bottom left corner, and the phase is the position where you start on the left edge. And if you hit the ball at an irrational slope angle, that means that the ball will have an infinite and unique trajectory that never loops. I think that this link with Lissajous curve can be retrieved with rectangle shape, and I'm even wondering what is happening with more complex shape. I hope that you are pleased to know the link between music, fraction, crown and pool table. And this is what I was talking about when I say that Lissajous curves can be full of surprise and with a lot of connection. So I will end here with this final revelation. I would like to thank Grant Sanderson for its Summer of Math exposition. This is the motivation I needed, I think, to start making video. So thank you for watching. I hope you enjoyed the video. Don't hesitate to subscribe and see you soon.